Okay, so hello everyone. Thank you for being here. So this is a kind of a so yeah, the title could have been longer or shorter depending on what I managed to cover. But I mean, this has to do with the notion of typicality, the connection with probability, how they're supposed to be explanatory, how that connects with the statistical postulate in statistical mechanics and the Boltzmann explanation, and then some thoughts about the GRW theory connected with that. So the context is the explanation. So probably this is going to be, you know, it should be okay. This is a philosophy of physics talk. I'm just going to be have all the formulas, but actually no. But I mean. So what I'm going to talk about is in the context of the explanation provided by Boltzmann and Gibbs about statistical mechanics. I mean, in terms of statistical mechanics, that has been summarized in David's book. That among the ingredients that it needs the statistical postulate. In this presentation, the statistical postulate, I will try to make sense of that in terms of, instead of being a postulate about probability, a postulate about typicality, as someone has suggested. So I will try to see whether where it leads us and make sense of, I mean, try to do my best of make sense of some of the arguments that have been raised in that respect. And so in the first part, so you can roughly divide it in three parts. The first part is that I will see whether it's possible to defend the idea that typicality is sufficient to explain macroscopic laws. Namely, you don't actually need to think of the statistical postulate as a postulate about probabilities. But maybe the notion of typicality, which is weaker, is enough to explain. The second part is regarding what about the postulate part of the statistical postulate name, right? So it's there is an argument that this has to be postulated because there are no satisfactory explanation for why that should be the case. So I mean, there are arguments out there that the postulate is derivable, what is called the postulate is derivable actually from the dynamics. So I will try to spell that out and see whether that is something that, how you can respond to objection to this. And so, at the end of that, if I have time, I will talk about the argument that was put forward by also David regarding the idea that in case of indeterministic theories in quantum mechanics, like typically the GRW theory, the statistical postulate may be dispensed with because the relevant probabilities are coming from the dynamics. Okay, so what I will try to say is that there is sufficient we can talk more generally, regardless about the type of dynamic, whether that is deterministic or indeterministic, whether we can generalize this typicality explanation. And if part 2 is correct, and therefore the dynamics can pick out the typicality measure, then it means that you don't need the postulate anyway, right? So you cannot really say, oh, GRW is better than the alternatives, because in that case, you know, you have less postulate than in the case of the deterministic case. Okay. All right. So Boltzmann, I mean, I'm just going to give you a couple of slides summary of what Boltzmann's explanation is supposed to be boiling down to is that the aim is to derive the macroscopic laws of thermodynamics in terms of the microscopic Newtonian dynamic, all right? And so that's supposed to, I mean, how do we do this? Well, there are technical problems and conceptual problems that we all know about, or if we don't know them, here they are. The technical ones is that, I mean, if you really want to do the exact calculation, that's not going to be feasible because, I mean, there are too many particles, there are too many things going on. And so what we do, I mean, according to Boltzmann, you use statistical methods. Namely, if the number of particles is big enough, right, you can just use these techniques to arrive to have some interesting information about macroscopic properties, even if you don't have an exact solution of all the n equations of motions and stuff like that. The conceptual problems that are relevant, but not so much for this talk, regard the fact that the microscopic dynamics is time reversible, okay, while of course the macroscopic work that we know about is not, right? We get older, coffee gets cold, and the opposite processes do not happen, right? So many problems regarding the statistical explanation. I mean, Boltzmann found a lot of resistance on that, but we now know that you probably can get over that. So the postulates that are needed according to the the exposition and the defense of David of this is that we need three postulates, right? So the first postulate that we need the dynamics, the microscopic dynamics, and so there are, this is standard terminology, so you divide up into microstate and macrostate. The microstate are, in phase space, which is the space of all the position and velocity of all the particles that you have. The microstate is a point in that. And the evolution of the microstate in time is the one that is given by the microscopic dynamics. And then you can talk of macrostate, right, in which you're just providing a partition of phase space into sets, right, which are macroscopically indistinguishable in the sense that if you want, you can assign to them properties like, for example, temperature, pressure, and stuff like this, right? That are, they vary very, very slowly on the macroscopic scale. So you can say, okay, this chunk of microstate, they all give rise to that kind of thing. So that basically there are many, many, many microstate for a given macrostate, and so given one macrostate, right? It is compatible. You don't know which one is the real one, right? Microstate you're in, okay? And so what happens is that I'm summarizing Boltzmann. There is one macrostate which is incredibly bigger than the other macrostate, which is called. This is a kind of combinatorially explainable to say, okay, count how many ways there are to have a uniform temperature. Then it turns out that that's the biggest of all. And so we call that the equilibrium macrostate. And so what Boltzmann did is, okay, define entropy, okay, because one of the macroscopic laws that we need to explain is the second law of the thermodynamics, which has, entropy in it. And so how can you define that in a way in terms of the micro description? Well, you just say, okay, fine. Entropy is defined as to be proportional to the size of the macrostate in phase space, right? So basically it's you count the number of microstate. Okay, so the fact, the idea is that the fact that the equilibrium state is so much bigger than the others will explain why entropy increases, right, in time for microstate which are not in equilibrium, and while remain constant for equilibrium state. Instead of reading that, just look at this. Okay, so this is what happens. So if this is phase space, right, that the gray thing is the equilibrium state. Of course, what's going to happen is that if this is outside of equilibrium, right? So this is microstate. Just go around, and so at the end of the day, sooner or later, eventually this guy will end up there. And when it's there, this stuff is so much bigger than the rest. Then it's just going to be very, very peculiar for that to get out. Okay, so what's going to happen is that it will stay there. If it's in there already, then what's going to say? So that means that since the entropy is proportional to the size, that it's just going to increase. Okay, there are so many more ways to go into bigger states, macrostates, than into smaller ones. All right. Okay, so from the fact that the dynamics is time reversal invariant, it turns out that, you know, if you ask, I mean, this is something that may take a while to realize. You may, I don't know, you may also see that immediately, right? But if you think about that, just like it, so it's going to be as more likely, so we just said, okay, so if you start from a small state, from a more macro state, you're going to end up into a bigger one, right? So if you wonder where you're going to go in the future, right, that's where you're going to go, right? But then if you ask, okay, what about the past, right? Where are you most likely to come from, right? You're more likely to come from a bigger state than a smaller state, right? Because exactly for the same reason. So I mean, just think about this in terms of this. I mean, of course, sizes are not really, I mean, you should think much bigger than this. I mean, so that's where you go from the past to the future, right? But where are you coming from, right? It's more likely that the past comes from a bigger entropy state than just that. So we don't want that, of course. That would be empirically inadequate, okay? And so, oh, sorry. So we need to eliminate the symmetry between the past and the future. We need to get rid of that, okay? And so one of the proposals that I think is the most sensible is just to say, okay, just postulate that at the beginning of time, there is an initial condition of the universe which is completely asymmetric, right? And namely that the universe started off with a very, 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 very low initial entropy, okay? So in that way, you can only go up. All right. Right, so I'm not going to talk about the past hypothesis here, except for another remark at some point. My focus is going to be about the statistical postulate, okay? Which is something that, you know, especially David and Barry have been working on, and in particular, I take it to be, I mean, this is what I take to be the upshot of what's going on. Of the reason why they think this is something that you need to have as a postulate, okay? So with the dynamics and the past hypothesis, what we arrived at is to the conclusion that entropy increases for the vast majority of microstate, okay? That's what's going to happen, right? I mean, you're going to go up, right? Why? Well, because, I mean, the ones that are just going to be conspiratorials are going to go up and then down and get out of the equilibrium are just very, very special. So most of the microstate, we're just going to be the kind of that we want, all right? So the second law of thermodynamics, which says that entropy has a high probability of increasing. So you're not going to show that entropy increases, period, right? In every single case, you're not going to do that. So you want to have a probabilistic version of the second law, all right? But you know, so we need to go from 1 to 2, okay? So we need to go from the vast majority of microstate, it's just going to go that way, to high probability, right? That's what it means, right? So we want to have some kind of a translation, right, of this. So, I mean, in order to go from 1 to 2, you need to be able to count the microstate, right, equally, right? So it's just like you will be using, you're not giving privilege to any of them. And so usually, so mathematically what you want to use is what is called the uniform measure. So the problem with that, right, is that how you're going to justify that measure. So why are you entitled to use that measure? Okay, so most, I mean, we already seen that the usual justification which is provided on this measure relies on the principle of indifference. Okay, so it's because you're ignorant about what the microstate is, then okay, right? It is, I mean, you're just dividing up them equally and just treating them equally, right? But you don't want that, right? That doesn't make any sense at all, right? Because your ignorance is something that has to do with you, right? And it's very weird to think that you're justifying and using that measure, right? and then because of your ignorance, right? You're just talking about the word, right? The word in itself, it has a dynamic, there are microstate and blah, blah, blah. I mean, regardless of whether there are people who know or do not know anything about them, okay? So you don't really want to end up in the situation in which our ignorance is influencing the dynamics of the macroscopic world. You don't want that, right? So what are the alternatives, right? And so, I mean, we just have that. That's a bad explanation. That's a bad justification. It doesn't make any sense whatsoever. So we postulate it. We have a postulate, right? You need to postulate. That's the right measure, okay? All right. So yes, so there are these two things which are involved in this. So first is the hypothesis that when you're explaining the second law, you're using the concept of probability, so that you're going to say that probability of entropy increasing is high, right? That's your that's what you need. You need the concept of probability. And the second one is that in order to go from vast majority to probability, you also need a postulate, all right? So there are these two ingredients. So what I'm going to do is try to explore the possibility of something different, right? So namely, maybe we can weaken our requirements, right? And maybe you don't need probabilities. After all, in this context, maybe what you need is just a notion of typicality, which is something that it's notoriously unclear about what's the meaning of that, and so part of the talk is just going to be on this. So the first part, what I'm going to do is just assume we need a postulate, right? So instead of specifying what that, instead of cashing out that postulate in terms of probability, let's just talk in terms of a typicality, right? So what I'm going to do is to try to argue that typicality is actually an explanatory notion, enough to for the purposes. I'm not going to try and argue that every kind of explanation is going to be a typicality explanation. That's not what I will be doing. What I will do is try to show how that typicality is going to be explanatory, in what sense, okay? And then the second part is just going to be, okay, fine, right? So, but what about the postulate part? That was the statistical part. What about the postulate part? The postulate part, well, is it really true that there are no other explanation rather than the principle of indifference, right? People have wrote about this, right? So is there a way of actually spelling out exactly what they have in mind and evaluate the argument with all the premises and in the order, and justify all the premises? And if you don't like one of the premises, what are you committed to? Something like that. And so the third part is, I don't know if I'm just going to go to that, but I mean the one I was saying before, right? If it's true that the statistical postulate intended as a typicality postulate can be derived from the dynamics, and we can extend whatever we said in part 2 to indeterministic theory, then we are not in position to say anymore that maybe GRW should be preferred. Okay, so the first part, typicality is explanatory or explanatory enough. All right, so this has to do, I mean, Isaac has a lot of work on this as well, so I will be talking about what he does as well, maybe twisting it a little bit, maybe hopefully not. Somebody should read his paper on this as well. So typical properties, just what the obvious definition is that. So if you're talking about an object or a system or a phenomenon, right? So a property is typical, right, of an object of a given type, if and only if the vast majority of the object of that type will have that property, right? I mean, that's just like straightforwardly so, right? So this is a gas, right? And so it's going to be typical for gases to expand. Yes, right. Most gases will have that. So the vast majority is the concept that needs to be a little bit elaborated on that, right? So what do we mean by this? Well, it seems like, I mean, if you read on the literature on typicality, that's exactly what they say. They say, well, the exception of that particular behavior, of the typical behavior, are few, right? So you measure, you count the exception, and according to the typicality measure, and the exception to the typical behavior are few. Right. Okay, so here's a something, you can just stop for a second and say, okay, yeah, but what do you mean? I mean, how is the probability different from typicality? I mean, when this is, can go on and on about this, but I mean, this is a few things that are, they will say how they're different, and it's just going to show that typicality is a much weaker notion. I mean, because in typicality, all you need is just you count the states, right, the measure, right? But also you don't need to be precise. So it's just a rough estimate, right? Probability is more, like, oh yeah, you want to make a difference between 0.4 and 0.41 and 0.43 or 0.1. I mean, the numbers in probability have an importance, right? But not in typicality, right? It doesn't have to, typicality doesn't necessarily have to, it doesn't have to be additive, it doesn't have to obey to the probability axiom, all these kind of details, right, are not, that's not required from a typicality measure, okay? So that's the definition, right, or at least what I understand it to be. So you need you just need that, very, very rough estimate, okay? Just need to count, right? And the measure has to be able to say what counts as very, very little, right? To make sense of this, right? Yes? Okay. Very few. Yes, exactly, right? So that's it, right? Entropy increases for the vast majority of microstate. Then you translate that into the typicality language, right? And just say, okay, entropy typically increases, okay? That's the idea. Good. So let's see. Okay, so let's see. What does it explain? Well, let's see. What we need to explain? Well, we need to explain the stuff that we saw before, right? In terms of not a vast majority, but now in kind of typicality language, right? So why is equilibrium typical? Well, because the measure of the macrostate which are not in equilibrium is much smaller than the macrostate which are in the equilibrium macrostate, right? That's the reason. You don't need to say, oh, right, how much, right? You don't need details, right? You just need that, right? Just gesture to the fact that the equilibrium macrostate is so big, right? That at the end of the day, they will end up there. How big? Well, I don't know, a lot, okay? And similar things in this case is, why do systems in equilibrium stay in equilibrium? Well, because the measure of the stuff that goes out, right, is much less than the measure of those who stay in, right? And why do systems which are not in equilibrium converge to equilibrium? Well, because the one that stay out, right, is much less than the measure of the one that go in, right? Right, and so, you can combine the two and just say, okay, why doesn't entropy decrease? Well, because for equilibrium states, it's typical for entropy to stay constant. And for non-equilibrium state, it's typical for entropy to increase. Okay? So that's, my understanding of how the typicality explanation is supposed to go. And how that's different. It's going to be different from a probability explanation. Okay? Of course, okay, just anticipating that. All right, so here is, if you want to have a schema of explanation, it looks like an argument. And so you can just say, okay, so this is an explicative schema based on typicality. So the explanation of an object or a process or a phenomenon or whatever having a particular property is given by the fact that the object being part of the particular set, and that set is having that property P as a typical property, right? So you can just say something like that. You can just say, look, right, X has some property, is in that set, right? Typically, all the members of the set has that property. Therefore, you have explained why that one object that you're thinking about has that property. Okay, something like that. Yeah, so that's the explanation of the gas, right? The explanation of this gas reaching equilibrium is that free expansion, right, is a typical property of gas, right? Great. Yeah, so this is just, again, right, remember, right, typicality is not probability, right? It just need you don't need a precise number, you just need an estimate. It doesn't satisfy the probability axiom. Okay, fine, but that's, I mean, how is that a good thing? I mean, come on, right? I'm just pretending to be on someone. It's something that I was asking myself at some point, right? Yeah, I mean, we don't want that, right? I mean, we want to have something like, I mean, we don't want to be able to say, oh, typicality is different from probability. We can just say, oh, entropy typically increases, but doesn't probably increase. We don't want that, right? I mean, that would be bad, right? Very, very bad. Okay, so I mean, a lot of work needs to be done to figure out exactly what the connection between probability and typicality, right? But the general idea that I think should be explored is that typicality grounds the notion of probability. Somehow you can just say, I mean, but I don't really know exactly if I should call it probability or, you know, credences or frequencies. But I mean, what do we talk about when we talk about probabilities? Just bracket that the name. But what I mean is something like this. I mean, okay, so we mentioned already that there are a lot of notions, right, going on here, right? So we talked about degrees of beliefs, we talked about empirical frequency, we talked about a bunch of stuff, all right? So what we want to be able to say is that typicality talk grounds our talk when we talk in terms of probability. So you want to say that, you know, when you're talking about degrees of belief, right? I mean, you can just say, you can think of that typicality that is a degree of belief of an observer making certain prediction, right? Regarding, I don't know, the behavior of entropy. Okay, so it provides a justification for such a degree of belief, right? But in contrast, I mean, the degree of belief is not going to help you out in understanding the regularities of nature because it's your degree of belief. And so we go back into the original problem of, you know, epistemology. Don't use epistemology to constrain metaphysics. Okay, so, but I mean, typicality doesn't have this. I mean, so if you just say, okay, typicality is prior to that and justifies degree of belief, then of course, whatever, I mean, when you're doing degrees of belief, you're doing epistemology, and now it's okay. So what about the empirical frequencies, right? I mean, yeah. So yeah, when we're making repeated experiments, right, we do obtain distribution of results, okay, and they show statistical features. So the idea is that if you can show that typically what is predicted approximates matches what is observed, then you have explained. Yeah, okay, so I mean, but I think that is just a gesture of what needs to be done to somehow compare the different notions and how typicality is supposed to ground probability, which I haven't done. But I mean, I think that if someone wants to go this way, they need to. Okay, so I mean, but talking about again coming back about typicality and explanation. So I mean, going back to the old times with the good guys, right? Okay, so it seems like we are giving an argument, so there has to be some connection between, you know, the usual covering law model, right? And we are using the dynamics plays a role. The dynamics is nomological. I mean, there has to be some sort of a connection between the typicality explanation and the usual Hempelian covering law model. Okay, so what about the deductive nomological model? Well, you can just rewrite the typicality in blue like that. X is an A, typically all A's are B's, therefore X is a B, right? I mean, of course, the DN model, I mean, the deductive nomological portion is just going to look like that. X is an A, all A's are B's, therefore X is a B. Okay, so both explanations rely on nomological facts, right? In some sort of governing facts, right? But of course, but these are exceptionless, right? And that's why the deduction goes through, right? These are not, okay? They're not. I mean, by definition, typically, right? It's not all typically. There will be exception, right? That's guaranteed, okay? So, and so they allow for exception. That's why you don't use that kind of explanation in the microscopic situations, right? When you can, I mean, if you have laws and you want, I mean, the laws are deterministic and they're exceptionless, then you just like deduce. But I mean, in case of the typicality schema, you can't do that, right? But by very definition, that there are anti-thermodynamics initial conditions. By the fact that typically doesn't mean all, right? It just means that the set of a section is small, but it's not 0. Okay. So yeah, so it's connected to it's similar to the deductive nomological model, but it's not identical. But of course, the natural suggestion that comes to mind is, what about the inductive statistical? All right, I mean, that is involving probability too, right? I mean, so what's the connection? I mean, is that the natural thing to explore? All right, so according to the inductive statistical model, right, you explain if you can just say that there is a high probability of the connection between the two things. For example, if a system of type F is explained of being also a G, right, by showing that the probability of an F is also being a G is high, right? So now you're not going to say, so you're just going to say X is an A, right? Probably all X's are B, therefore X is a B, right, with high probability, right? So I mean, example, right? Red apples have a high probability of being sweet, and this explains why this red apple is sweet. Okay, that's sample. Typicality, I mean, of course, you take out the probability and you get the typicality, right? Locution. Red apples are typically sweet, and this explains why this apple is sweet. So the structure is exactly the same, or almost exactly the same. I mean, they're very, very similar, right? They are very, very, very similar, but of course, they are different because because probability explanation, you are specifying what is the strength of the inductive process going on, right? You do this, and Hempel was thinking that only high probability will be explanatory. I know that now people are thinking differently, but that's what's going on in Hempel, right? And in the case of the typicality explanation, that's not necessarily that the two explanations they're the same. So there are certain probabilistic explanation will not result as typical explanation. The only thing that you need to ensure is that the probability is not high. Okay. So the fact that for a particular decay have a probability equal to 0.5 explain why this nuclei of type X has decayed, but that would not be a typical event. Okay? In order for a typical event, you really need much more than that. You need a very high probability for that. So this is what I'm tempted to say, right? And I'm not sure. That's what could be the case, that inductive statistical explanation with large R, with large probabilities, are actually typicality explanations. Okay, so the details do not count, right? You don't care about probability being 0.2 or 0.3 or 0.7 or 0.2 or 0.2 or 0.23 or whatever. And also, when we probabilistic reasoning, to say, oh, you're giving probabilistic explanation, right? So usually when I given in a probabilistic, when the word probability is presented to me, oh yeah, think about this, I'm just freaking out because I think of probability, I find probability explanation and probability reasoning in general very, very counterintuitive, right? Think about Bayes' theorem, right? How many people are going to get that wrong about what are, then of course you go through and you understand, right? But and in the case of the typicality reasoning, that's the opposite, right? When they invoke the explanation which invoke high probability do not seem to be as counterintuitive as the others. Okay, so what I'm trying to say is that when we're presented with inductive statistical explanation with large R, what we actually have in mind is a typicality explanation. Think about stereotypes. And I'm not saying the stereotypes are explanatory. I'm just saying that usually, there are a lot of cases in which we take stereotypes as being satisfactory explanations. Okay, so when I meet with my girlfriends, right? We go to the coffee shop, and we've been talking and talking. I mean, and if I come up and say, okay, well, typically men are jerks. I mean, everybody's just yeah, right? And that's supposed to, yeah, right? And of course, you guys do the same. I mean, exchanging the gender, the relevant gender or not. I mean, whatever. But you know what I mean, right? So, I mean, we regard stereotypes as as a satisfactory types of explanation. And I couldn't resist the joke, so it's just going to be there. So what I want to say here, I forgot where I am, of course. Right. So yeah. So I mean, at some point. So here's a remark, right? So that the explanation based on typicality is compatible with the deterministic dynamics, right? Or the kind of a causal structure, right? But that's not. That of course doesn't happen in the case of statistical mechanics, in which typicality is really. The fact that there are anti-thermodynamical states, right? You're not going to be able to show that all microstate. You're just going to show that the vast majority of them are like that. Right. Okay. So, all right. So you're explaining a phenomenon. If you're explaining that the property that he has is typical. All right. So, what kind of explanation is that? Well, that of course it's just gonna be important. You're just gonna buy this or not, depending what you think a satisfactory explanation is gonna be, right? But think about what people usually require for satisfactory explanation or adequate explanation. Just say, okay, it's gonna be informative, right? So when I'm looking for when I'm presented with something, and that I'm just gonna is that an explanation? What I'm looking for? What I'm looking for. Informativeness, right? I want to be, and not only that, I also want to have, conciseness, right? So I'm just going to say, it is typical for entropy to increase, right? It's going to be informative and simple, right? It's just going to tell you a lot of things, namely what happens to the vast majority of microstate. It's just going to leave out very few cases, right? And it's just one sentence, right? Typically, entropy will increase, right? Three words, even shorter than that. Okay, so what about the connection between explanation and prediction, right? So, well, given a typicality explanation, what should you expect? What should you predict about the behavior of stuff that you have shown that have a particular typical behavior? Well, that they will do that. Right, so typically gases expand freely, right? So we have good reason to predict that the next gas is gonna expand freely, right? Okay. Another thing that people usually connect to explanation, and certainly Hempel did, and certainly Jean Brickman does. Is to say, it's to say that something is explanatory if it removes the surprise element. Okay, so the phenomena is just going to be explanatory if you're not surprised to see that. Okay, so that's what Hempel called expectability, and that's a feature that, according to some, a satisfactory explanation should have. Does typicality explanation has this? Does it have this? Yes. Sure, right? Typically, gas is expanded. Are you going to surprise when we see a gas expanding? Of course not, right? That's what typically happens, right? Typically, salt dissolving water. We are not surprised. And this, of course, needs to be, what's the contrast, right? Well, of course, the contrast is what if we see something like a monkey randomly this is the typical example. Randomly typing on on a computer writing this beautiful poem or the Divine Comedy or something like that. Right? This is compatible with the dynamics. There is one initial condition that will make that true, right? So, I mean, if you just have the dynamics and the initial condition, you have accounted for that. Okay, but if you think that expectability is a notion that is important for a good explanation to have, that's very surprising. So that's not a satisfactory explanation if you think that this is an important criterion. Yes? Okay. And it's interesting to notice that people are actually trying to. Thank you. Oh, no. That's all right. At least I turned. Right. And so the fact that people do not like to be stuck with just saying, oh yeah, sure, there is one initial condition ad hoc and cherry picked that will give rise to that particular phenomenon. So of course, I mean, it's not incompatible. I'm not gonna jump outside of the window. Oh, I failed. No, I didn't fail. I mean, that's accounted for, but I mean, it doesn't sound, really explain, right? That's connected to the expectability thing. And this is common practice in physics, right? So the inflationary model was developed just because of that, or arguably because of that, at least this is what people developing that reported as their motivation for going. Because the Big Bang requires very special initial conditions, right? The inflationary model will make that condition typical. And so it seems like that's the fact that you want this expectability thing as a characteristic of a good explanation is compatible with what's going on. Right. So, okay, probably this occurred to you already. It's something that it's very obvious. If you think this way, then you're in really big trouble, or at least. People who think that, they recognize that that's exactly one of the issues to work on, right? So to get rid, so what happened is that what about the past hypothesis, right? We used that, we introduced that to get rid of the symmetry between going to the future and going to the past, right? And so we said, okay, right, just postulate that the past hypothesis is the initial condition is that, right? But it's very, very low. It's very, very cherry-picked. Right? It seemed like we ended up in a situation in which we explained something being typical by using this atypical initial condition. So how's that good? Right? And of course that motivates, right? That explains why people are trying to work on this and try to say, okay, maybe, right, there is some explanation, right? Namely, presumably a typicality explanation, or maybe even, with probability 1, that would explain why, right? For the vast majority of initial condition, we end up with that kind of past hypothesis. Okay. Right. Okay. So this has to do with. So here's an objection that has been raised to the typicality approach that I'm aware of. Frigg and Rendell, they said, well, the typicality approach as it was discussed, right, is just like independent of the dynamic. It doesn't take the dynamic sufficiently into account, right, because it just says, oh, right, equilibrium is the biggest, right, that's a matter of size, that's it, right? We already had that joke, so. What they want to say is that no, you need more, right? You need to show not only that the initial condition is typical, you want to show that the dynamic has a role, and for the typical dynamic as well as for the typical initial condition, you will get entropy increase. Okay, so they want to say, look, the dynamics in the presentation that I gave so far doesn't play enough of a role because it just was a matter of dimension of the equilibrium state. So we have a theorem, and that's what it says: typical initial condition and typical dynamics. All right. Right. So that's what Badino calls the combined typicality approach, right? And so. So, but I mean, see, here's what I would say, right? Okay, so do we really need this, right? Well, I don't think so. Why not? Well, because it seems like if you just say, oh, typicality of the initial condition and typicality of the Hamiltonian, right, the dynamics, right, then you're going more general, right, because you're not typicality of the initial condition at all, only, right? But I mean, what the fact that the dynamics never arises in the discussion that I presented before is that no matter what the dynamics is, right, it will go up if it's Hamiltonian, right? It will end up in the equilibrium state. So it's not like the dynamic is ignored, right? It's ignored because the theorem is true for anyone, any dynamic whatsoever, right? So in a sense, right, it's not the theorems that they prove are nice, but they're kind of useless, right? Because they're actually more. The original typicality approach is more general. At least that's what it seems is going on here. So, well, I don't know how long, but for sure part 2 a little bit. I'm just want to talk about. All right, so the part 2 was, okay, so the first part was typicality is explanatory, maybe we don't need probability. The point of that was you don't need details, right? And typicality doesn't give you details, so just go for typicality. This one is, okay, what about the postulation part? Well, people have said something like this, right? The dynamics picks out the typicality measure. How? That's the argument that I reconstructed that you can find in a few lines here and there in the papers of the typicality people. This is the one that I took from Shelley's paper, and I reconstructed this way, right? So the purpose of the okay, this counting, can be done at different times. I count it now, and then, yes. But why privilege this over this? There seems to be no reason, all right? So the initial time is just conventional, right? So from the first three, the measure should be invariant under time translation, okay? Right? So the next step is, okay, if the dynamic is Hamiltonian, okay, the measure must not depend on the form of the Hamiltonian, right? The measure should be generic. And then what it turns out to be, at least according to their math, it's the only generic stationary measure is the uniform measure, okay? And that's why the uniform measure is the measure of typicality. Not because it's uniform, but because it is stationary and generic. Yes? So the idea is from symmetry consideration or genericity consideration and and the dynamics, you get the typicality measure. Yes? So that's the idea I get. So objections to that. Brickman, are the one that has engaged with this argument the most. I haven't seen many people engaging with this, and I think more people should engage in this, because if it works, I think it's a big deal. So Brickman says, well, no, right? Think about chaotic system, right? Dissipative system, right? So what happens is that if you use the stationarity argument, that gives you the wrong measure, right? The typicality measure is the uniform measure, but it's not stationary, right? It's not. In that system, right? That's mathematically the case, right? So according to him, we should use the uniform measure on Bayesian grounds, right? Which is, to me, too reminiscent of, the principle of indifference. So I wouldn't agree with him that that's the right choice. But assuming that so we need another criterion, not the stationarity criterion, all right? But suppose that this works. So you say, hey, for non-Hamiltonian system, we choose this using on Bayesian grounds, right? Non-Hamiltonian systems are more general than Hamiltonian systems. So whatever criteria we use for non-Hamiltonian system should translate into the Hamiltonian case. Therefore, and since in the non-Hamiltonian case we don't use stationarity, stationarity is not, it's the wrong, why you need another criteria to pick the typicality measure. Okay, right. So I think this is a very interesting argument, counter-argument. Yeah, counter-argument. So I tried my best to respond, and here's what I came up with. And you say something like this, okay, sure, okay. Stationarity doesn't seem to be the right notion at all for dissipative systems. I mean, of course, they're dissipative, right? I mean, right, so I mean, we shouldn't really be surprised about that. However, what about this? I mean, is it really true that non-Hamiltonian systems are more general than Hamiltonian ones? Well, it depends on what you mean, right? I mean, now what we're interested in is to describe the universe, okay? And so is the universe Hamiltonian or non-Hamiltonian? Well, the hope is that it is Hamiltonian, right? And we're using non-Hamiltonian system to describe subsystems, right? Which are not closed, okay? So I would say that we don't, so we reverse his argument, just say, look, Hamiltonian systems are more general insofar as they correctly describe the universe. So we use the stationarity argument to pick the typicality measure for that, for the universe, okay? And then when we move to pick what is the right typicality measure for subsystems, we don't have to pick it again, right? We already did, right? We know what the typicality measure is because we use the stationarity argument for the big system, right? For the small system, we don't select it again. It's what it is, right? Oh, it's not stationary. Yeah, so what? It's not stationary, but we don't need stationarity anymore because it was already picked before. Does it make sense? Well, that's what I think could be an answer to him. He didn't like it, but I mean. Yeah, okay, thank you. Right. Okay, and then another objection that he has in print is something like this. Well, stationarity, well, what kind of odd notion. It's very far from from our intuition about explanation. We don't use that, right? It's not, right? He mentioned sometimes in two monkeys talking about this, they don't talk about stationarity. So the idea is when we are providing an explanation, somehow you need to provide, the explanation that we provide needs to match our intuition. So if you provide an explanation which we would not regard as intuitively as an explanation, the theory of explanation has failed, right? Like in case of Hempel and the flagpole and right? So we want to, right? So the notion of stationarity is never part of our intuition while explaining. Therefore, stationarity cannot really be part of the scientific explanation at all. Okay? All right. Okay. Right. So I wasn't particularly impressed by that because, just of course, right? I was impressed by the first. I had a hard time with the first one, but this is just like, no, it doesn't matter, right? It was just demanding too much, right? What we care about, the explanation is the result, right? So we have this explanatory machinery, right, over there, right? And then we plug it, right? And then we say, at the end, the output is the explanation. What we want is that the explanatory output matches what we intuitively regard as an explanation, right? So that's what we care about, the matching with the intuition. But in the machinery, the box, whatever pieces the machine is using can be far away from intuition, right? Otherwise, we don't get out of, any kind of explanation that we provide in physics will fail. So we go step by step, and we get far away, right? So stationarity may be counterintuitive, but it is connected to the idea that no temporal instance should be privileged, right? And that is intuitive, right? That's why we require stationarity, right? And typicality uses this intuition, right? But it implements it through the notion of stationarity, which can be mathematically sophisticated, blah, blah, blah. But it doesn't matter. It's the refinement of that idea, right? You need that piece of mathematical thing to make precise that. But it is capturing the intuition. All right. So, yeah, I lost track of what I'm going to do. So, I mean, the one that I think, okay, what about the genericity, right? You can just complain something like this. Nobody has actually complained about that, maybe because it wasn't really specific. I mean, I don't know. But I mean, here's something that someone can say, oh, why do you need a genericity, a generic Hamiltonian, right? Why do you care? How many Hamiltonians are there of the universe, right? How many are there? Right, exactly. So, I mean, why require the genericity at all? Yeah, I mean, and also, I mean, I think that is also kind of, I don't know. This is what I came up with, and then you can tell me how to improve it or not. Just tell me that it's just like hopeless. So I have two things, right? One is just to say, well, it is true that there is one universal Hamiltonian, but there are a lot of effective Hamiltonians that we're using all the time, right? When you're describing systems which are not the universe. So what we want to have is have the same result, that the results match, right? We don't want to have mismatch. Right? And so maybe you can say, okay, that's where the genericity comes in, right? Regardless of the Hamiltonian you're going to pick, the one of the universe, the one of the subsystems, you need the same result, okay? And then at the end of the day, I think that that's exactly where the theorems of the Frigg and Brendel are pointing at is fail, because it's the genericity of the Hamiltonian. Just say, okay, it's generic Hamiltonian. It doesn't really matter, right, which one you're going to pick. It's just going to be true for all, right? And that's exactly the point in which it comes out. It comes up, right? So if you require genericity, then you can claim that the dynamics doesn't matter. Okay. Right. Okay, so what I was trying to do is to try and show how typicality, non-necessary probability was sufficient to explain the macroscopic law could be. What people mean when they say that typicality measure is not postulated, but it can be derived from the dynamics using this consideration about symmetries, right? And so if so, then you can just say, okay, fine, right? Explanation, Boltzmann explanation is reduced to two things, right? The dynamics and the past hypothesis, okay? The dynamics itself determines the typicality measure of phase space, and then the past hypothesis that we cannot get rid of up to now. I think I have no more time, right? Right?
If you're aiming for an hour, you have about 5 more minutes.
Oh, okay. Well, okay. Okay, I can just gesture about the last part. All right, so what about if we try and extend this to the classical case, we extend the classical case to the quantum case? So in some cases, for example, in Boltzmann mechanics, you can see how the departures can be minimal. But what about when the laws actually change in nature? They're not deterministic anymore. What about indeterministic laws? And David says, well, things change a lot, right? If the laws are the GRW laws, what happens is that they are exactly, the GRW law is such that you can claim that the statistical postulate comes from the dynamics, in the sense that when you're talking about probabilities, you're talking about the quantum mechanical probability in the GRW law. Okay, and this is that may be a reason to say, okay, this is why I like GRW better than the others. It has more. Okay, right, and so the next step that one can explore is to say, okay, right, but what we have done so far is that for deterministic laws, if they work, right, what I've been doing works. For deterministic laws, the dynamics picks out the typicality, so you don't need the statistical postulate. All right. So can we extend this view to indeterministic laws? Well, it seems like straightforward. You cannot, because the space of, indeterministic laws can be conceived as with a fixed past and an open future. So how are you going to do this? There are ways in which you can try and generalize and select a phase space for an indeterministic dynamics that doesn't necessarily rely with this picture of a fixed past and future. And if that works, then you can just say, all right, so you can generalize and say, also in the case of the indeterministic dynamics, the statistical postulate comes from that, or in the case of the typicality postulate is selected from that. And so if so, then there is no additional reason to prefer GRW over its deterministic alternatives. But I guess that's for another time. And so I'm just going to stop here. I have a thank you slide. Thank you.